Well, welcome to our course on system engineering. Some would say that system engineering is a difficult course to be teaching. Hopefully, as a result of what we've gone through here, you'll get some insight and see the breadth and possibilities that come along with it. So there's going to be a number of textbooks that I'm going to be using for this course, or at least going to reference them. And I'm going to spend a few minutes just to introduce those before I get into some of the detailed lectures. So the first textbook is The Engineering Design of Systems, Models, and Methods. And Booty is the author of that, Booty and Miller. This has an interesting perspective on it, that it tries to be focusing on the process and includes a lot of insight into some tools. So what they're focusing on is model-based system engineering. And so that's going to be a key distinction for what we're going to have in this course. So what they do is they try to consider the key system engineering design activities. And since they're involved in industry, working on a variety of different projects, a lot of government related projects for a number of different agencies. So that's going to be stuff that we'll see in the textbook. And so it's divided into 3 sections with an introduction, an overview, and some basic knowledge of system engineering. Then we'll get into the design integration and then supplemental topics. And so that's the first textbook that we'll be using. The second textbook is really a very informative primer into what SysML, the system modeling language. And in this course, we're going to actually do some hands-on modeling using SysML, using a readily available tool that there's a community version of visual paradigms that we'll be leveraging. And so this is a practical guide. It's a very detailed book that walks through each of the various elements of what SysML is. And it also has some of the individuals that have been very involved in the development and further refinement of SysML. So once again, this is going to be delving a lot with model-based system engineering. So I think that's going to be a useful textbook. Another textbook, which is really relatively speaking, a short handbook, is something called SysML Distilled. And this is another individual who has been involved in industry for a long time. And so this is a handbook. And if you notice, it also has a foreword by Steiner, who is also one of the authors of this main textbook that we'll be using, the Practical Guide to SysML. And this is going to be more focused on the satellite area, which is something that we're going to be focusing on in this class. And we'll be developing a SysML model for a CubeSat or CubeSat related aspect of a CubeSat mission. So that's going to be something that we'll be leveraging from this textbook. And also they have a companion website where they have a model. And this is something that we'll be using in Cameo Systems Modeler. There is a demonstration mode for that you can download for academic use, and it's something called DelSat 77. So we'll be seeing that in our course. There are a couple of other general references that I want to be pointing out to. And so this and the next textbooks are trying to just give a better view of what system engineering is in general, not necessarily model-based system engineering, but the whole system engineering process. And so NASA has developed a system engineering handbook. This is the 2nd edition. It's available free for download, and there will be a link in the course. I know those viewing this lecture won't be able to click on this link. And so it's trying to provide a general guide on how system engineering is done for the NASA community. And so the NASA has a particular bent in how this works in terms of their process and methods. And you'll see that as we develop in this course. And finally, this is an excellent textbook. And if it was a little bit more focused on model-based system engineering, I would have made this the main textbook, but this is really has a gold star in terms of the breadth and the complete presentation of what system engineering is. And so I really recommend that you consider getting a copy of this. And it's a System Engineering Principles and Practice. There's currently in the 3rd edition. And so definitely a very broad textbook that covers the whole system engineering process. It also has a chapter on model-based system engineering, and so that definitely is something that it includes. But due to the fact that we wanted to be more focused on model-based system engineering, I chose to have as a primary text something else. So those are the textbooks that we're going to cover. And so Booty will be the main textbook we're going to be using. And so that will be creating a framework for how I'm going to model these charts that we'll be using in these different lectures. But just keep in mind that there's a lot of other textbooks. And so just for this introduction, I'm just going to finish up with these few key points that Booty mentioned in his textbook, 12 engineering designs of systems themes. And so this is characteristics of the kind of stuff that you will find in Booty. And so first you want to do by finding the design problem in system engineering. So you need to be thinking it from a high capability point of view. So that's the first thing that you want to be doing as you're contemplating doing a system engineering model or process. So you have to define the design problem. And then the design problem in system engineering has to be brought into terms of requirements. This is a key thing, is how, and the requirements are actually what you're going to be building to. And so you have to architect what the requirements are and come up with a process for how that's going to make sense and relate to the overall functional capability that you want. Number 3, the design process will fail. The requirements are defined too narrowly. You need some flexibility that as you get into the design process, there will have to be some give and take. You may have some requirements that are, although are noble, but maybe not realizable with the available technology. And so those are some things that will have to take place as you start to get into the design process. Number 4, for the design problem to be well-defined, the evolving set of requirements must be complete. And what that means is that you want to make sure that you cover everything. You want to make sure that they're consistent, that there's no contradictions in the requirements, that they're correct, that they're valid for what would be an acceptable solution, and that they're attainable, that you actually have the technology and means to make that happen. So these are all the things that are important that you want to be getting your arms around as you're starting to do the system engineering design and development. Number 5, the characteristics and requirements will not be achieved as scenarios defining how the system is used are not elaborated in detail. So you need to be coming up with use cases, use scenarios, and then you start to play that out. And this is a great way how you can be engaging with your customer, your sponsors, the people that have given you the go-ahead to do this design. Number 6, the design problem is not likely to be well-defined as the requirements do not address every relevant phase of the system's life cycle. So it's one thing to design something, it's another thing to have things operational and also to have it be in such a way that it is something that can be maintained and eventually decommissioned when that is necessary, or have some type of an interim type of block change or upgrade. So those are all things that need to be thought about. Number 7, the design problem is not well defined if the requirements do not contain stakeholders' preferences. You need to make sure that you echo exactly what the people that are paying for your system, what they want. Number 8, the key to understanding many of the modeling techniques for developing requirements, defining architectures, and defining requirements are found in discrete mathematics. This is an interesting thing that Booty mentions in this textbook that typically my experience hasn't been thought too much in terms of the system engineering process. And so we're going to include this And so you'll get a chance to get some insight into this, and you can make your own judgment if that's a tool that you would want to be using in your toolbox of system engineering, and how and when that might become useful. Number 9, integration requires a well-defined design, including a design of the qualification process for verification, validation, and acceptance. So you need to be considering those things, thinking from an integration point of view. Number 10, early validation of the evolution of the definition of the design problem needs to be pursued vigorously. As you go along, it's very likely that the definition of the design problem will be changed. You'll get more insight as you start to be fleshing this out. And so that's an example of something where model-based system engineering can definitely help. Number 11, qualification of the system is a key issue in integration. So how are you going to qualify? You have hardware. How are you going to come up with this process that your stakeholders are going to agree upon to determine what is something that is acceptable? And so that's going to be important. And finally, successful qualification also requires that decisions about what should be tested be made in a systematic way that balances the two conflicting objectives of not wasting resources and yet while obtaining stakeholder acceptance. So you want to be working with your stakeholders, but you also want to be efficient with your resources. And so that can be a little bit of a challenge. Okay, with that, I'm going to end this introductory lecture. Thank you very much.